Hi everyone and welcome to CPS on a Thursday. As seems to be the tradition with the Thursday lectures, we've managed to get somebody from across the ocean, which we never would have got if we weren't virtual. So it's a really good opportunity. We've got Dr. Shaughnessy from America, who is a radiochemist and the PI of the heavy element group at the Lawrence Livermore National Laboratory. She completed her studies and PhD at Berkeley in California, and she previously worked at the Lawrence Berkeley National Laboratory under Heino Nietzsche, moving to the Lawrence Livermore National Lab in 2002. And while there, she was involved in the discovery of 5 super heavy elements. And this is the focus of the talk tonight. I'll pass over to you. Thanks.
Thank you very much. Let me share my slides here. Turn this on. Okay, well, first of all, thank you very much for the invitation to come and speak today. As you said, it's always a little tougher for us to come overseas just to do seminars. So I guess with all of my putting down Zoom, the one benefit of Zoom is now we can have this discussion together. I'm Dawn Shaughnessy. I'm currently the division leader for nuclear and chemical sciences at Lawrence Livermore National Laboratory. That's a shot of the lab in the upper left-hand corner. Just to give you some orientation, we're in California. We're about 40 miles east of San Francisco, so we're not exactly on the coast. As you can tell in the picture, there's no water, but we are considered what they call the San Francisco Bay Area, which right now means most people that the cost of living is ridiculously high, and that is because we are also about an hour away from Silicon Valley, which is south of us. To give you some orientation. Our laboratory works on a lot of different projects spanning a wide variety of areas. But one thing that we've been involved with for many years is the heavy element program. And so I'm going to be talking to you today about that. I'm going to start with a little bit of background on why people started looking for elements in the first place and what we then did to discover them. Okay, so I always have to start my talk with a periodic table because I'm a chemist by training, so that's the most important thing. And this is how it looks today with our 118 elements. All have official names now, so this is accurate and complete. And of course, as these elements have been discovered, they were put in the periodic table really just numerically. Once something was confirmed to have a certain number of protons, it was just put in up the next number until we filled the chart. And later in the talk, I'm going to discuss a little bit what we're doing to try to get at some of the chemistry of these super heavy elements, because as you know, really the placement in the periodic table should not be numerical. It should really be based on their chemistry, and do they follow the same chemical trends of their heavier homolog elements. So we're trying to get at some of that. That's very difficult due to the fact that these are all short-lived radioactive elements. But let me start first with some background on discovery and then move to the chemistry later. So now I'm going to jump back in time. So last year, actually, sorry, 2 years ago, was the 150th anniversary of Mendeleev's periodic table, which I'm showing here. And there was a big international celebration about that. And I bring this up historically because when you go back in time and look at the periodic table and how it's evolved, really they started a certain way, and then Mendeleev was the first one who put these elements in based on their mass and started to recognize this repeating chemical properties of the periodic table. And if you look at the chemistry, there were obvious places where elements were missing. So this was really the first time that anyone looked and realized that there were elements that had yet to be discovered. Now, of course, in this case, most of these were naturally occurring. But what's interesting to me is always to look at the bottom row where you see he has uranium, and then there's elements past uranium. So even at that time, it was understood that there could be and should be elements that extend beyond what was then the known periodic table. So now I'm jumping ahead quite a few years to 1945, and the father of the modern periodic table, so to speak, Glenn Seaborg, there shown on the right, who was at Lawrence Berkeley Laboratory. He was the one who recognized that the actinides should be their own series. And you probably have learned about this, but in case anyone's not aware of the history, when the actinides were first in the periodic table, they were included in the main body under the transition elements, and it was thought that they would be row 7 of the transition elements. And Seaborg and his team realized that the chemistry of the actinides was quite different from the transition metals, and in fact, they align much better with the lanthanides, being primarily +3s until the lower ones are not, but the upper ones are all +3s. And so he moved the actinides down to this actinide series. And in fact, this is what earned him the Nobel Prize in chemistry, was this actinide concept, not for his discovery of plutonium, which he also was responsible for. But now when you look at this periodic table, it becomes even more obvious that not only do we have many more actinides that should be discovered, but then you could come back to the main body of the periodic table and then have a true row 7 now, where you have chemical properties analogous to their nearest neighbors. So Seaborg and his team really started this search for new elements, and that could be a whole other talk in and of itself about the actinides and how they used early nuclear reactors to bombard uranium, to make neptunium, and then the early cyclotrons and particle accelerators were used to bombard those actinides with deuterons and alpha particles. And as you know now, they marched all the way up through the actinides, and in fact started to get beyond the actinides. And so we jump now ahead to 1969, and this is what the periodic table looked like. They had already gone all the way up to element 104, which is now Rutherfordium. And the question at this point was, how much farther could the periodic table go? And you have to go back and think about the technology at the time, because they had cyclotrons, they had particle reactors at this point, but they weren't as energetic, or I should say have the intensity that they have now. So it was much more difficult for them to bombard materials to get to that next step. And I'm going to discuss how we actually make a new element a little bit. Also, detection. So at this point, they were using a lot of gas-filled detectors. Solid state detectors were, in their infancy, they didn't have great sensitivity or resolution. So it was getting more and more difficult with the technology in the 60s to push much past element 104. But they recognized that they should be there just because of the repeating nature of the periodic table. The question was, did we have the technology, or when would we have the technology to get there? So now I have to take a step and dig into the nucleus, because really this is nuclear chemistry. And we have to talk about the nuclei for a minute. Just in case people aren't aware, I'm going to give nuclear physics 101 in 3 slides that you need to know. Probably most of you know that elements can have different isotopes, which means that the number of protons is always the same, but the number of neutrons can change. The example here is hydrogen, which has 3 isotopes. And we have to start thinking about the actual protons and neutrons, because much like the electrons, they also have similar properties in that they want to be paired. They want to exist in a shell structure, just like the electronic shells. There are proton shells and neutron shells. And so there are certain numbers of nucleons that make a nucleus particularly stable. And when you have odd numbers of nucleons, or you have unfilled shells, this is what leads to the nucleus becoming unstable and making it actually radioactive. And there's different kinds of radioactivity that can occur. And again, the whole point of something being radioactive is to make the nucleus into a more stable configuration. The main one we have to talk about when we are dealing with transactinide elements is alpha decay, shown on the left. This is where a very heavy nucleus will actually spit out an entire helium nucleus, relieving itself, so to speak, of 2 protons and 2 neutrons, and actually changing the atomic number of the nucleus that's left. So you actually are changing the element in the decay process. Another type of radioactivity is beta decay, where you're actually emitting an electron and converting a neutron into a proton in the process. This is how tritium decays and becomes helium-3. The other form I don't have on here that's important for transactinides is fission. This is where we have a very large nucleus, something like plutonium-240, shown on the left, and it actually splits then into 2 roughly equal fragments. One's usually a little bit heavier than the other, but they're 2 large fragments, and there are some neutrons that follow that as well. Now, the next slide, I have to apologize for the color scheme, because it was originally created for a very large stage with a screen, and it looked gorgeous up there. On the computer monitor, not so much, but what you're looking at is a demonstration of radioactivity. For people who are colorblind, this is probably the worst slide you've ever had to see in your life. But what you're looking at is on the left, we have a certain nucleus. They're colored yellow on my screen. And when we talk about radioactivity, and half-life is the time it takes for half of that sample to transmute into something else through radioactive decay. So the middle, we have about half yellow and half purple, and that's 1 half-life. On the right-hand picture, they're mostly purple. Now it's 2 half-lives, and so on and so on and so on. And this is important because as we go across the actinides and then into the transactinides, the half-lives are getting shorter and shorter. So uranium, which is the heaviest naturally occurring element, is radioactive, but the half-life is millions of years. So that's why we see it. Once we move even from uranium to plutonium, we still have quite long half-life, but nothing like we see in uranium, and so on until we get to rutherfordium, element 104, which, I think if I remember correctly, is somewhere on the order of hours to days. So you see there's a drastic shift in time as we progress across the actinide elements. Okay, so now let's get back to Glenn Seaborg. This is a picture that he drew again in the late 60s after the actinide concept was known, and they'd already discovered the actinides at this point. And what this is representing is the protons versus neutrons on this plot. And as I mentioned before, there's a nuclear shell structure very analogous to the electrons, just like the noble gases are very stable because they have this closed electronic configuration. So it is with nuclei, that if you have closed shells of neutrons or protons or both, then you will have something that's much more stable and much more resistant to radioactive decay, which means longer half-lives as well. So what this represents are these so-called, we call them magic numbers. Really, they're just the closed shell numbers, if you will, of nuclei. So put them here. There's at nickel, which is Z28, There's a lot of isotopes of nickel that are very stable because it has a doubly closed shell configuration. The next magic number heavier than that is Z equals 50. So you have tin there, which has, again, a lot of isotopes that are very stable because of this Z equals 50 closed shell. And then you get up to lead at Z equals 82, which is the same with its magic number of 82 protons. And so they knew about this with the shell theory of nuclei, which had changed. Originally, the idea was that nuclei were more like drops of liquid, and you could define their mass based on the properties of a liquid drop. It was called the liquid drop model. And then they changed and realized we now have this shell structure of nuclei. And the question then became, what comes next? So they knew this theory, they knew these elements, and they knew that they were naturally occurring. And so the search became, where's the next magic number? And you see in this interesting map, which I like to use, there's this person standing at the end of the actinides, willing to slingshot him or herself onto the magic island, which was predicted at the time to be at element 114. Now, because you have massive proton numbers, you would need many more neutrons in the nucleus to make it stable, because you have to, if you just have 114 protons, the Coulomb force will blow it apart. You have to have neutrons in there to keep it together for some period of time. So the theory said that if you had element 114 with 184 neutrons, you would be a doubly magic nucleus. And at the time, the theories thought it could be so long-lived because of this enhanced stability that it might exist in nature. And if you go into the literature, there were indeed searches for element 114 in nature that, of course, came up negative. But the question still remained, where was the next closed proton shell? Was it at element 114? And could we find it? What was the half-life, and would we be able to find it? Now, getting to actual modern times, so to speak, not that the 60s aren't modern times, but modern times probably for most people on the call. There were very few places that had capability to do these experiments. Berkeley was one. Lawrence Berkeley Lab was engaged in this quite heavily. Russia at the Flerov Laboratory for Nuclear Reactions was engaged in this heavily, as was the GSI lab in Germany. And it got to a point where things had stalled. What had happened is Berkeley went beyond element 104, and they marched up really 104 and 105 and 106. And then they kind of got stuck. And it's because of the specific technology they were using. And then the GSI lab in Darmstadt, Germany really took over at that point. And they did a different kind of reaction. And I'll talk about these reactions in a second. But Germany was then able to discover element 107 and marched all the way up to 112. And then they got kind of stuck. And so at that point, everyone was really stuck. So 114 was just a couple elements away, and nobody could seem to get there. So in 1989, there was a collaboration formed between the Livermore Lab, where I work, and the Flerov Laboratory in Dubna, Russia. And it was formed because Russia had, at the time, the most intense particle accelerator in the world. But they didn't have the detection needed to look for these very short-lived elements. And Livermore likewise didn't have a particle accelerator, but they had the expertise in the targetry and the detection. So they formed a collaboration. And you have to think back, probably most of you are of an age where this may not have affected you in your life, but this was at the heart of the Cold War still, that this collaboration was formed. It was very unusual for Russians and Americans to do anything together, let alone collaboration like this. but it remained in collaboration for many, many decades, actually, and is still somewhat going on, although a little bit less today. But it's because of this collaboration that we're able now to talk about elements 113 and beyond. So let me get there finally to the last part of the transactinides. So how do we do it? Well, it's really just as simple as figuring out where you want to go and combining protons to get there. So for instance, let's say we want to make an element 116, which is livermorium. If we start with a beam of calcium ions, which has 20 protons, of course, and we have a target of curium with 96 protons, if we bombard those together and get a complete fusion of the two nuclei, we will have, for at least a short period of time, an element that has 116 protons in it. It may not be very stable or stick around for long, but if it stays around long, just long enough for it to be detected, then we can say for at least that period of time that we had created an element with 116 protons, therefore a 116. So often the issue is, what do we use for the beam, and do we have material for the target? The beams that we used, and oh my goodness, my chart's out of date on this page. I'm embarrassed now that I don't have the one with the names on here. But the ones we've used for elements 113 to 118 was calcium, and the calcium was chosen for a reason. Element 20 is also a magic number. So the plot I showed you started at 28, but there are actually smaller magic numbers as well. So calcium at 20 is equals 20 is a magic number. And the specific isotope of calcium that we used for the beam was calcium 48. So it has 28 neutrons. So it is a doubly magic nucleus. And why is this important? Because the calcium 48 ion itself is so incredibly stable, when it hits the target and it's coming in with a lot of energy, and I'll talk about that next, we don't want so much energy in the system that it just immediately disintegrates before it has a chance to fuse and be detected. So the calcium, being doubly magic itself, comes in with less excitation energy than something that itself would be more unstable. So the calcium 48 is specifically chosen for that purpose. But then it means we have to use actinides as our targets, as you see here. We're very fortunate that at Livermore, there was a lot of legacy material available to make targets. We had plutonium-244, which is a very rare isotope of plutonium. We happen to have a gram of it at Livermore. We also had some americium and curium that we were able to use as targets. When you get past curium, though, it gets a little tricky because berkelium has a half-life of about a year. And so there's not stockpiles of it that you can use. So it's made as a byproduct of californium-252. So californium-252 is produced for a lot of industrial uses, things like well logging and other areas. And the berkelium is a byproduct. So at Oak Ridge National Lab, which is in Tennessee in the US, they sometimes are able to pull the berkelium off of the californium. It's very difficult. They have to do it all in big giant hot cells with remote handling. But if they can do that, then the heavy element groups around the world can use that berkelium for a short time as a target. And that is, in fact, why element 17 is named tennessine, because the berkelium target was produced at Oak Ridge. And without that, there would be no element 117. And I'll wrap this slide up quickly by saying that, Einsteinium is another one that's very hard to get. So people look at this and say, well, can't you just do element 119 by bombarding an Einsteinium target? there's not enough material around to make a target. So with this particular method of calcium-48 and an actinide, we have hit the end of what we can do, unfortunately. So it's not just the target material and the beam, you do need to figure that out, but you do need a powerful particle accelerator because again, the purpose is we're trying to bombard two nuclei together and have them completely fuse, which means we need to overcome the Coulomb barrier between them and get them to fuse together. So this is the U-400 cyclotron that's at the Flerov laboratory in Dubna, Russia. And this is the most intense blowtorch, if you will, of calcium-48 available in the world. And that's why the experiments were done there. So the way a cyclotron works is there's two magnets in the middle that are in the shapes of the letter D. So they're called the D magnets. And there is the field between the magnets is oscillated so that it accelerates an ion through the magnets. And as it goes in the diameter of the cyclotron, it gets to higher and higher velocities as you alternate the current between the two magnets until finally you get it to an energy where it can overcome the Coulomb repulsion when it hits that target. And it's traveling at the end at a fraction of the speed of light. So to give you a sense of scale, there's the ion source, which is where the calcium is actually heated and ionized to create the beam. There's where the target would sit in there somewhere behind that red circle. There's the cyclotron is behind there, and then there's a beam line that comes down where it hits the target. And then that's just scientists for scale. So you see, these are big instruments in big buildings, which is why we can't just have them pretty much anywhere. You know, some people at this point say, well, what about hospital cyclotrons? Those are much smaller because the point of a hospital cyclotron is usually just to bombard something with, you know, lower energy particles, not heavy ions like calcium at large speeds. So this is the cyclotron. The larger the diameter, the more energy you get. This one's 13 feet in diameter. The largest cyclotron is at Triumph in British Columbia, Canada. That one is 56 feet in diameter. Okay. Next for the target. So in the middle there is the picture of the actual curium target that was used in the 116 Livermorium experiment. It is electroplated onto a backing, or it can be deposited onto the backing through just deposition or vacuum deposition, or even just, I don't want to say painting because that implies a paintbrush dipped in something, but you can just apply the material to the backing as well, depending on how thick it is. And we have this on a wheel. And the reason why it's on a wheel is because as the beam is hitting it, we have to rotate it at very fast velocity, because otherwise, if the beam just hits a stationary target, it'll just burn a hole through it and keep going. So the wheel is rotated to try to dissipate the heat load from the beam. And, you know, so there's a watch there for scale. So you can see these aren't huge targets. But we still need quite a bit of material to cover that wheel with at least a layer. You want a layer of material thick enough that the beam will interact with it and not just pass right through. So after the beam comes out of the cyclotron, it hits the target, what happens next? Well, due to conservation of momentum, the reaction products get spit out the back of that target, where they then are put through this separator. This is called the Dubna gas-filled separator, or DIGFERS. And it's a series of magnets that are set so that the low mass products, or I should say the low Z products, are steered away. Things like the beam itself that didn't react, particles that just get kicked off. And then the heavier particles are allowed to then transmit through the magnets themselves to the detector. And the detector, which is shown on the right, it looks like an open shoebox from the side, and is covered on all sides with silicon semiconductor strip detectors, which are sensitive to both timing and position. So what happens is we have, let's say we have made a heavy element. Our beam has come in and it's hit our target and it's fused, and it's come through the separator and it hits the detector. It's then going to undergo its radioactive decay. And because the nucleus is so big, when these things undergo alpha decay, again, that's the spitting out of a helium nucleus, there's very little momentum transferred to the parent nucleus. So it stays where it is. So it's sitting in this detector, it's embedded, and it's undergoing decay. And every time there's a decay, we can record that signal. And so that's what we're actually looking for when we're looking for a new element, is that series of decays that are correlated in time and position in this detector. And so here's what we call a decay scheme. This is just an example, again, using 116 livermorium. We have our fused nucleus, which would implant itself in the detector. And usually it spits out a few neutrons because it does have some excitation energy just from the reaction. So it's formed in an excited state, and it will emit a few neutrons. So we end up with something like this 116 isotope 293, which is sitting somewhere in our detector. It then undergoes a series of alpha decays. And each time it undergoes an alpha decay, again, it's changing its element. So we go from 116 to 114, and then 114 to 112, down to 110. And then once we get to 110, which is Darmstadtium, the nucleus actually undergoes fission and it splits apart. So that's where we lose the signal, because the fission fragments do have enough energy to move, and we then can't track their decays elsewhere. So we lose the chain. But this is the kind of signal we're looking for in a heavy element decay. And actually what we do is we go backwards. We look for those fission events because there's fewer of them. And we work our way back in time and space in the detector and see if we can get to a parent nucleus that looks something like what we're expecting. Now you'll notice the half-lives of these, which are listed in the bottom of each square, are getting very short indeed. So even our element 114, which at some thought originally would be in nature, only has a 2.6 second half-life. So things have to get through that, both the separator and into the detector very quickly, which they do, and then we can look for these decays. But there is a very low probability of success. That is because, again, we have a Coulomb barrier we have to overcome. We also basically need a head-on collision. If the calcium comes in and just grazes, say, our curium nucleus, if it's a 116 reaction, it might just kick it out, or it might undergo a different kind of reaction where instead of completely fusing, they just transfer particles. So those are the things we don't want. So if we start with, over the course of an experiment, we'll use about 10 to the 18 calcium nuclei. In the end, we might get 0 to 3 atoms of the heavy element of interest that we have been able to produce and successfully detect on the back end. So these are very high patience experiments. The cyclotron is often running 24/7, just running the calcium beam into the target. And then people both in Livermore and in Russia simultaneously were looking at the data, trying to tag these fission events and go backwards in time to get to the original product. You're not always successful, but when you are, of course, it's extremely rewarding. So how do we detect a single atom? And I love this version of the periodic table because it shows what every element really looks like until you get to things that we cannot really hold in our hand, and then it's just who it was named after. And this one also is not up to date. I will have to fix that as well. But the question is, we are making literally single atoms. So how do we know, that we've seen something? And later, I'll talk about chemistry, but to give you a preview of that, if we don't have a mole of atoms, we don't have anything macro that we can measure in a bulk property. So how do we measure a single atom's chemical properties and link it to its homologs in the periodic table? That's something that people have been working on for a long time as well. So luckily at Livermore, we have some of the world's fastest supercomputers, which always helps everything. And what you're seeing on the right is an actual set of data from the element 117 experiment. And because this data comes 24/7 and there's so few events, we thankfully use the computers to try to track for us an event that looks like something that what we're looking for. So now what I've highlighted in blue is an actual tennessine event where there's a fission and followed in time with a series of alpha decays. So that is how we look for elements. They're not the fun way of doing chemistry like Glenn Seaborg did, but using computers and data as everything is now. Okay, so where are these performed? Well, I mentioned some of them already. The one I didn't mention at the time was Riken in Japan, which actually has credit for element 113, nihonium. And then the Flerov Livermore collaboration has been given credit for elements 114 through 118. So this kind of sums it up from Berkeley. Berkeley is about 30 miles northwest of us here in Livermore, so that red X is pretty close to where we are. That's where it all started. And then the blue X up in Russia, in Dubna, which is about a 2-hour drive from Moscow, that's where everything ended in terms of the periodic table. Now, the big question is, did we get to the magic island, the element 114, doubly magic nucleus? And the answer is no, because unfortunately, we don't have enough neutrons in the system. So remember, the magic nucleus was predicted to be 114 with 184 neutrons. We are not there yet. We are at 175 neutrons, so we're almost 10 neutrons away. And the problem is that we don't have combinations of targets and beams that afford us a neutron-rich system so that we can get closer. But what we are seeing is that we are at the edge of that next closed proton shell, because what this chart is showing you is the longest isotope that's been discovered for 104 through 118. And if you look at those numbers, as you go along from, let's say, you get into 110 and Darmstadtium, and you start to march up, you're in the seconds range, and you get to 114 flerovium, and you're in the 2 to 3 seconds range, and then it drops drastically at 115 moscovium down sub-second, and you get all the way to 118, you're sub-millisecond. And that drop is so pronounced. And the reason why is because that is the end of the effect of the shell. The closed shell isn't just at 114 and 184. It's really an area of nuclei around there. And so we're seeing the edges of that effect even in the nuclei I've listed here, because we have something like element 112, which can last almost 30 seconds, which is kind of crazy when you think about it, that it can live that long at that heavy a nucleus. And it's due to this shell effect and the fact that we're seeing the edge of it. So how do we get to heavier things, or more neutrons in the system? It's a good question people are asking. One way is to try to change the beam. And there is a facility coming online next year in Michigan, here in the US, called the Facility for Rare Isotope Beams. It will be a radioactive ion beam facility. The cyclotrons now basically accelerate stable nuclei, that is an accelerator that will be able to do radioactive nuclei, and hopefully they can get their intensities high enough someday where we might get to these more neutron-rich systems. Okay, I real quick want to talk about chemistry because it's actually the thing I get the most jazzed about. So we've discovered all these elements, and as I previewed earlier in the talk, do they really belong where they are in terms of chemistry? They're there numerically, but what about chemistry? So if we look at the chemistry of the transactinides, 104 and 105 showed some interesting effects. And what happened is they did a lot of extraction experiments where they went through an extractant, say with zirconium, and then hafnium, and then rutherfordium 104. And based on where they are in the periodic table, you'd expect a certain trend in extraction. And what they saw is when they got to 104, it inverted, meaning that it didn't go in the same direction, but it actually went in an opposite direction. And the same thing happened with 105. And the reason why is because of something we call relativistic effects. So these massive nuclei are so big that they're actually able to accelerate the inner shell electrons to near relativistic speeds. And what happens then is that those shells will contract, shielding the nucleus essentially so that the outer electron shells expand. And it also can change the mass. So it changes the bonding properties and it changes the mass of the atom. So the chemistry does not follow straight from what you'd expect just going down a chemical group. So this was a big deal and people were very excited about relativistic effects until they got to 106, which 106 through 108 behave exactly as you'd expect. In fact, there was a Nature paper, I think the title was something like, ordinary seaborgium or something like that. It was basically that if they went through the chemistry, they did exactly as you expect. So the chemical theorists who do this area of the periodic table, and there's a few of them around the world, get very confused at what's going on because you have relativistic effects dominating early, then they seem to go away. The problem is we can't do chemistry very easily starting on 110 and higher because the half-lives are getting to be very short. So how do you do chemistry on something short-lived? You have to do something that it's not going to be an equilibrium system, but something that will extract your nucleus or your atom, I should say, very quickly and allow you to detect it. And we're not able to say something about the chemistry of that single atom. What we can do is infer based on its homologue. So if you're doing an experiment, let's say we want to do a flerovium 114 experiment, we would look at the chemistry of tin and lead and flerovium and see if it follows either of those. And then can we infer that it behaves like a tin or a lead? Or this is where the theory gets very interesting. Because of those closed shells around 114, the predicted closed nuclear shells, there are some predictions that flerovium would actually be like a noble gas and it would be totally inert. And so if that's the case, what does that mean for our periodic system? It means it would be something I can't even imagine. So what we've been trying to do at Livermore is come up with some novel molecules that we can use to extract a single atom. We're looking particularly at kind of crown ether structures. This is a little bit older slide now. There's some different structures they've been trying. The idea is that the extractions are very rapid and you can fit your element 114 in the middle of one of these and try to detect it. The experiments are very challenging because you have to do it at a cyclotron. So you have to continually try to make your product. You have to transport it to a chemical system. And when it comes out of the cyclotron, it's in a gas. So now we need that gas to somehow get dissolved in a solution. So we're working on a system where we're actually going to dissolve that gas into a solution and then run that solution through an automated chemistry system. And it has to be automated because we're talking a few seconds. And this whole thing has to happen before the 114 decays in 3 seconds. So we're talking very fast transport. we're talking very fast extraction, non-equilibrium systems. But if you run this over and over and over again, and you do it on its homologs, then you may be able to infer what a 114 chemistry looks like. So I'm almost done with my slides here. Just real quick, how far can the periodic table go? I heard an interesting talk, now it's back in 2019, that Professor Pico gave. He's a theorist who's been working on this for a very long time. And he showed this incredible periodic table where he said, if you forget about real life, as theorists often sometimes do, if you forget about production and you forget about the mechanisms of how these things are made, just from a purely theoretical point of view, he said that a periodic table should be able to go up to an element 172. Now, of course, the reality of us seeing this is really probably slim to none because of the low production rates I told you about and the short half-lives. At Oganesson 118, we're sub-millisecond, and you're making one atom every few months or so. The way the Japanese and the Germans do it, I should very quickly note, is a little bit different. Instead of using calcium with an actinide, they bombard lead or bismuth with beams accordingly. They do that because, again, the lead is a magic nucleus, so it has less energy in the system, so there's less chance for it to disintegrate. It's what they call cold fusion, but not the cold fusion that was around back in the 90s. It got everyone all spun up, but cold fusion meaning there's low energy in the system. That's how elements 107 through 113 were discovered. And to give you a sense of production, the Japanese 113 experiment lasted a year to see a couple of atoms of 113. So that's where we're at with real life here. There have been searches for 120. They have not been successful yet. They've been able to set some limits. What they're working on right now, so Russia's building a new accelerator, and it should be coming online any minute, if not already. That's going to be even more intense than the U400 that they've been using. And they're also working with Oak Ridge National Lab on titanium beams, because we've kind of run out of what we can do with calcium. So titanium would be the next logical step. It's a little bit harder to make a beam out of titanium chemically, but they're working on it. The idea being, if they can make it, we would go back to the actinides and just march through. And that's how you could start with your elements 119, 120, and so on. So do I think that we'll make those elements? Probably. Someday we might see a 119 or 120, but I think it'll take a while because we have to make some shifts to the paradigms of how we do heavy element discovery right now. And again, these radioactive ion beams may get us closer to the shell. So what do we need in the future? More intense cyclotrons. The Russians are working on that. New beams. People have been working on that. Germany is as well, I should say. And then the detectors and the electronics. I mean, if we're getting sub-millisecond, we right now are getting also held up by how responsive our electronics are. So things are getting better with digital electronics and all that. And then chemistry is somewhat behind the discovery, of course, and there's some new ideas there too. There's people looking at chemistry on a chip, because you're looking at a single atom. Can you just do something in a microliter solution and make your detection and your extraction all in one chip? New molecules and automation. And if it's not as easy as Tony Stark made out in Iron Man 2, but it is being done. So I think with that, I just want to put up the teams of people that worked on our heavy element projects. This is back when the 117 experiment was done, and this is how many people were needed to discover element 117. So these are large multidisciplinary international groups, and the chemistry is just as intense. So we're going to keep plugging away and see where we get. And with that, I will thank you very much again for the opportunity to talk about this, and happy to take any questions.
Hello, can everyone hear me?
Mhm.
So I'm Kresh and I'm gonna I'm gonna chair the Q&A session here, but before I do that, I really want to thank you for this mind-blowing talk. It's absolutely fantastic. And I have tons of questions and I'm afraid not many are relating to chemistry, but before actually I start shooting at you with questions, I would like to invite our audience actually to ask some. So is there anyone who has any questions here? I guess everyone is just blown away as I am. Is that possible? Yeah, okay. So this is actually so exciting that I had to take notes. I never do that during talks. And again, I hope you'll forgive me for being a little bit ignorant about the chemistry, because you mentioned that you're really excited about that bit. But I mean, the scale of the whole operation just blows my mind. And I have a lot of questions about that. And I guess, I mean, where do I start? What is the most delicate part of the process and how long, I mean, how long does it take from, okay, we're gonna make this and it's gonna take, I don't know, how long does it take to actually go from, you know, okay, let's do it to, hey, we get it?
Oh, sure. It depends on the element. So for, let me say the early ones, early for us being like the 114, which is the first one that Livermore was involved with Dubna. That, of course, took quite a long time because the whole detection scheme had to be done. It had to be made from scratch. The material was available, so that wasn't such an issue, but getting the detection scheme going, that had to be done. And the most, I'd say, the worst part in all these experiments really is trying to get then the material overseas to Russia, because often the targets are highly radioactive, and let's just say it's not trivial to get a barrel of radioactive material shipped overseas. In fact, there was one drum of americium which sat at the airport for almost a year because they just couldn't figure out a way to get this stuff where they wanted it to go. So that is often the hardest part, which surprises people. I think they want me to say something about the data and all this, and all that's challenging, but really just it's often just the logistics of the simplest thing that really hang you up. So that can take a long time. And then once everything's running, so once the material's there and they've started the beam, it's really then just a matter of luck. Sometimes you might get something right away. Sometimes it takes months and months. So these experiments are months long, and you're just continually looking at data. Luckily, we write scripts that go through and look for certain signals and all that. But the experiments themselves take many months, and getting the material there can also take many months. So let me say that those are, for most things, the longest parts. The one caveat to that is the element 117, because of this berkelium issue. So Oak Ridge Laboratory doesn't routinely pull berkelium from their californium. So this was a huge effort where they had to go to our Department of Energy and ask permission to do this. We had to find funding from various sources to do this. And they didn't have many people left at Oak Ridge who had experience doing this, because it had been many years. So they had to basically resurrect this whole process of going in the hot cell and pulling out this berkelium. And then getting that to Russia was a feat in and of itself. So I would say from the first discussions of element 117, it was several years before the first atom was actually being measured.
Okay.
So I hope that answers your question.
Yeah, it certainly does. And we have more questions pouring in the chat, and I will just read them out to you as they come in, okay?
That's fine. My computer's lagging a little bit, so I can't get to there apparently.
Okay, so Mike was wondering what the motivation is behind looking for new elements.
So there is this whole magic number is really the first motivation, because the theory in this area is just fascinating, and we really don't know, what beyond element 114. There's a lot of questions about, does the theory of the nucleus itself actually change? And so discovering these things and getting the data that then feeds into the nuclear theory is very important. And then there's the whole chemistry question. Do these things really behave like you'd expect, or are they somehow in the wrong place? And I've heard talks given on that too, about what would the periodic table really look like if we used the chemical properties of these things and shifted things around. So really that's the motivation for doing this, is to get at, what are these next set of magic nuclei, and then how does it affect our knowledge of the periodic table and the nuclear theory in this region. And besides that, I just got to say it's very cool science, and it's fun to do as well.
I bet. So the next question is, so is it necessary to use magic number elements for nuclear fusion? And if so, why?
So it's not necessary. It just, what it does in these cases of making these elements is it really just gives us a better probability of getting that compound nucleus we're looking for. If we come in with something, for instance, that has, too many neutrons or too many protons for, what its normal stable configuration is, it's just going to bring so much excitation energy into the system that we really lower our chances. And some of those experiments have been done. For instance, there was a 120 search many years ago. Well, many years ago, I'll say probably 10 years ago, where we used iron beams, and it was iron plus plutonium, and we didn't see anything. We had to set a limit. And likely one of the issues, again, is that the iron was not as stable in its nuclear configuration as is calcium. So it probably brought in too much energy so that it couldn't fuse. So the short answer is it's not required, but we increase our probability if we use a beam that's more closer aligned to the magic numbers.
Okay, and then the next question would be, can antimatter heavy elements be made?
Probably theoretically they can. We know that for any matter, there should be equal and opposite antimatter. And that gets into areas of research. They do this in my division, looking for dark matter and why is there not enough antimatter, and I will leave that to them. You can get a future talk from them, but that's getting out of my wheelhouse, so to speak.
Okay, thank you. And then the next question is whether it's likely that some of the superheavy elements were made naturally at some point after the Big Bang.
Oh, most definitely. The fact that we can make these now and repeat it, that they're not fluke things, that anyone with the same target beam and accelerator can reproduce the same properties over and over again, means that this is the physics of what these things really look like. So absolutely, after the Big Bang, or maybe even in a supernova, these things likely are made for some very short period of time. And then the problem is, of course, now they just decay as soon as they're made. But yeah, absolutely, they're probably produced.
Thank you. And then the next question is, do you think that any elements with a filled 5G subshell will be synthesized in our lifetime? And are there any assumptions about their chemistry, if such chemistry exists?
Well, I think we'll definitely get to, let me say, elements probably 119 and 120, just because they're working on beams and there's better cyclotrons and we're getting there. So I think at some point in the future, we'll probably see that. Beyond that, it's really hard to visualize, because now we're getting to such short things. I'm not sure we would have the technology to see it, but I never want to say never. But in my lifetime, I'm guessing that's about as far as we could go, is probably to about a 120. Assumptions about chemistry. we always start off assuming that they follow the periodic trends of their group. The chemical theorists, are always looking at how relativistic effects may affect the chemistry of these things. And are they going to have some crazy inverted chemistry compared to their homologs in their chemical group? We always start off assuming they'll follow their group, but we have been shown in the past that that is not always the case. So it's really a case-by-case basis.
Thank you very much. And could you please comment on the transition from using calcium to using titanium? So what the reasons behind it are?
That is just to get higher in proton numbers to try to push past 118. So again, with this, there's two kinds of experiments that are done. There's the kind that the Germans and Japanese did where they're bombarding lead and bismuth. Then there's the kind we did with the Russians, which is bombarding actinide targets. So being that we can't make a target of anything heavier than really about californium, we have to now go up in proton number in the beam because we can't increase our target anymore. So the titanium now is just to go back to our actinide target set that we have and start plugging away, trying to get at the 119 and above.
Okay, thank you.
Oh no, computer, do not reboot now. Okay, go ahead.
The next one is, could inorganic polymers be used to trap the new elements?
That's kind of along the lines of what we're thinking for chemistry on a chip type processes. The person working on that now at our lab, he's been fixated on sort of using just these single molecules, but they have to be on a backbone of something. And so the idea is now, can you make a chip where you have some kind of inorganic polymer on the chip and then put your, affix your molecules to that backbone and then just flow your solution through it and hope that you catch your 114 as it flows through. And if you make, for instance, the back of this some kind of scintillating material, you could do liquid scintillation at the same time. If that all worked, that's in development and it's TBD in the future, but if that all worked, you would absolutely have to have some combination of polymer backbone with these specific molecules on them and then with some scintillating material behind it.
Okay, and do you envision a future in which these super heavy elements have a practical application?
Not at all. Just to be totally honest, I used to say, oh, never say never, but we're getting to half-lives that are so short. Other than defining, the practical application is it will define chemical and nuclear theory beyond the known matter right now, which is pretty cool in and of itself. Back when they discovered some of these, I'm sure they didn't know if there'd be application. And then, of course, americium is used in almost every smoke detector we have. Californium is used for things like, as I mentioned, well logging. So there have been applications of some of these elements, but now we're in the second and sub-second range. So I can't imagine too much that we could do with that.
So they're super exciting and useless.
Pretty much.
Okay. So there's another question, and it is from Tom. And Tom asks, so what sort of chemical reactions are you looking at? You mentioned briefly some host-guest chemistry, right? But is there anything else that one could do?
So what's happening in this area right now is primarily gas-based chemistry at the moment. Mostly the first reason being that they can flow the gases much faster. So if you're looking at very short half-lives, you have a chance to detect something. So in Germany in particular, they've been looking at gas phase of element 114, trying to see if it is more like a radon, or is it more like a lead, or is it more like something completely different. And what they do there is they have a set of detectors that they keep on a temperature gradient. And so they will run this first with radon, so they know where the radon will deposit. They'll run it with lead, they know where that deposits, and gold and other things. And then they do the 114. The experiments so far have been a little inconsistent, so they haven't really been able to say yet that 114 behaves this way or that way. But the reaction there is really just deposition onto a temperature gradient. So it's not a specific reaction, but more of just a behavioral reaction, I will say. And then, for us in the aqueous phase, we're just looking at extraction right now because, again, it's fast. Can we just extract into a particular phase with a known cavity size as opposed to not extracting because something is, not behaving a particular way?
Thank you very much. And I am wondering, where are the greatest challenges, in the next step? So is it developing analytical methods and instrumentation that can actually follow what you're doing, or is it the actual experiment? What is it? I'm curious.
The technical challenges of the next steps are all of those things and more. It is, we need different beams, and that's not as trivial as it sounds because there's an ion source that heats the material to ionize it and transport it in a gas and make a beam. But some materials don't ionize like that as I'll say, as straightforward as calcium does. So titanium has been a challenge because, if you know about titanium oxide, it doesn't like to dissolve or react with many things. So how do we now make a beam of titanium? So they're working on the novel chemical forms of titanium that could be used for beams. So that's the first challenge. Then there's the cyclotron itself. This is why the Russians have built a new one, because the intensity of the beam they can produce, the number of atoms you make goes as the intensity of that beam, the number of target atoms, and the cross section, namely the production rate of making it. So the cross sections we know are very small. The target atoms are what they are. So the only variable we can play with is that beam intensity. So that's why they're building a whole new cyclotron just for these experiments, essentially. And then target material, in that if the titanium beam doesn't work, is there a way to get Einsteinium? They used to make Einsteinium decades and decades ago, but it was never really in massive quantities. So do you try to stand up an entire production of Einsteinium? That's probably not going to happen. So really it comes down to beam material and beam intensity. The detection, electronics, all that comes into it as well. But with the advent of digital electronics, things are much faster there. So I don't think that's going to get pushed too much more.
Thank you very much. I definitely think you should try and have a look at the chat, because the feedback is mind-blowing. And you have even people from Australia getting up insanely early to listen to your talk, and they say it has absolutely paid off. Has anyone else any questions? I will take that as a no. And before I hand over to Miranda, I would like to thank you a lot for this really inspiring, interesting, mind-blowing talk. Actually, that's what it is. I said mind-blowing a couple of times, but that's what it is. Thank you very much.
Thank you again. This has been very fun.
Miranda,
Thank you. I just like to reiterate our thanks again for speaking to us today. It was absolutely fascinating. And also thank you to everyone who attended, those from UCL and those from outside. We're really glad that we could open our events to everybody this year. So I'm just going to stop the recording now.